Good morning, everyone. Thanks for joining us this morning. We will be going through our physics marathon. Now, we won't be able to cover every topic on the syllabus, but we'll try to see how many topics we can cover in the short period of time that we have, and we hope that it is beneficial to you. Right. So my name is Omari Brown. I am going to be the main tutor moderator for this session. I attended Herbert Marson Technical High School and I got a grade 1 in CSEC physics and both units of CAPE. So I do have some experience with what I've been doing, and I've been tutoring for the New Jamaica Foundation for about 3 years. No, I studied actuarial science at the University of the West Indies. So if there's anyone that's interested in that particular field of study, you guys can reach out to me if you have further questions, right? Right. So during our session today, communication is going to be key. There are times when I'll be asking persons to answer questions a bit more conversational. Now, most of the answers are already pre-typed within my slides, and I'll provide the slides to you guys at the end of the session, right? But as I said before, it is better for you guys to be in the live session where you'll be able to ask questions and get answers almost immediately. From time to time, I'll be asking volunteers to read, and if we should notice any errors in my slides, I'm just asking persons to make the slides, right? So this is what I'm hoping to achieve today. So by 11:25, I'm hoping that we'll finish the 2023 paper, and then we will look at some select questions for another hour and a half thereabout. Select questions will include topics like magnetism and a few others. Don't remember all of them off the top of my head right now. As it relates to feedback with you guys, I don't mind if you open your mic and speak because I don't currently have the chat open in front of me while I am sharing in full screen. However, when you're not speaking or asking a question, just ask that you guys remember to mute your mics, turn off your cameras, and just to be respectful to each other in the chat. Now, everyone won't always know the question. Sometimes persons are going to say the incorrect things. I might even say the incorrect thing. And if you have a problem with what I say to you, then you should definitely open your mics or say something so that we can address it. I can make mistakes wherever you have been to, whether it's a previous marathon session, the person could have made a mistake. And so if you disagree with a solution, it's best for you to say something, right? Be the brave one, say something and learn, and don't just hope that someone else will ask your question for you. Right. So just some exam tips before we start. Please use a calculator that you're familiar with in your exams. Different calculators, they're programmed differently, and based on how you input numbers into the calculator, you might get different answers. So it's best to use a calculator that you are familiar with. And I always recommend that persons prioritize questions or areas that they're strong on, leave the difficult questions for last. Maximize on the marks that you can, and then afterwards worry about anything else. And just avoid wasting time. You have roughly 1 minute and 30 seconds per mark. And CSEC doesn't deduct marks for incorrect answers or for additional information, right? But don't waste time. Don't waste your time giving too much information for a 2-3 marks question or a 1 mark question, right? So now let's jump into it. We're 1 minute behind. So CSEC 2023 paper, and we're going to start with question 1. And so I'll begin by reading. So figure 1 shows the setup for an experiment to determine the specific heat capacity of 300 grams of a liquid using an electrical heater. The heater has a power rating of 105 watts. Temperature and time data for the liquid in the polystyrene foam cup are shown in table 1. We have our table of values there. First question says to define the term specific heat capacity. Second question says to assume that all the electrical energy produced by the heater is transferred to the liquid and that P is the electrical power of the heater. T is the time duration of the experiment. M is the mass of the liquid. C is the specific heat capacity. And delta theta is the increase in temperature of the liquid. And we're to deduce the formula which represents the heat energy transferred from the heater to the liquid. So the first question, what is specific heat capacity? And I'm throwing it out to persons in the session. Somebody can just open their mic and respond. What do you think specific heat capacity is? What do you know it is? Right? Quick, easy, 3 marks question. You're going to answer. Go ahead.
Sorry. Specific heat capacity, C, is the heat energy required to change the temperature of unit mass, 1 kilogram by 1 degree.
Right. So it's very important there that you mentioned 1 kilogram because specific means 1 kilogram. So you have to mention that. And again, you have to say by, did you say 1 degree temperature? That's what you said, right?
Yes, sir.
Right. Now, that degree temperature can be in Celsius or Kelvin. It doesn't really matter because 1 degree change in Celsius is equivalent to 1 degree change on the Kelvin scale. But for using standard units purposes, you can just say 1 Kelvin, right? But that's pretty much all that you would need to say for a 3 marks question. The only additional thing that I'd probably add is just to state the units, right? So that's joules per kilogram Kelvin. Right. And the formula is going to be power times time is equal to mass times our specific heat capacity times our change in temperature. And using the symbols that they gave us, it's going to be PT is equal to MC delta theta. Now, it's important that you use the symbols that they gave you in the question. Most times, persons use capital T instead of theta, right? But it's important that you follow the instructions and use the symbols that they give you. So easy, 3 marks, 4 marks there. Moving on. Using the grid provided on page 7, plot a graph of temperature theta versus time. D, calculate the gradient G of the graph. E, given that gradient is equal to P divided by product of MC, calculate the specific heat capacity C of the liquid, express your answer in SI units to one significant figure. And then afterwards, they want us to determine or to say what we believe the identity of that liquid is based on the table of values that they gave us. And then finally, we're to state a precaution that we should take when performing this experiment. Now, generally speaking, whenever you're given a graph question on CSEC, it is imperative that you read the entire question before plotting your graph. And that's because sometimes CSEC might say to you to determine the corresponding value for a specific temperature. So in the table, they gave us down to 56.8 degrees Celsius, but CSEC could have easily said, how long will it take for the temperature to raise to, or the temperature to get to 65 degrees Celsius? In a case like that, you'd want to have 65 degrees Celsius on your graph. So it's always best to read the entire question before plotting anything, right? So I'll just start by just identifying some of the precautions while we're here, and then I'll go back to my graph to show you what that should look like. Precaution: the liquid should be gently stirred before taking the temperature reading, and that's to ensure that the heat is distributed through the entire liquid. You don't want to be taking the temperature at the top part of the liquid, which is going to be colder than the bottom part of the liquid, or the part of the liquid that is closest to the heater versus the part that is furthest away. So you want to ensure that the temperature, the heat is properly distributed in the liquid. And again, ensure that the bulb or the thermometer is immersed into the liquid. The bulb should not be partially submerged, right? When you get incorrect values for your answer. Right, so I think someone said that they're not hearing anything a while back. That person should just leave and rejoin if they're still not hearing anything. Right. All right, so this is my graph. You guys are going to be drawing on an actual sheet of paper in the exam, but I'll be showing you guys pretty much a computerized image, but you follow basically the same principles. As I said, please ensure that your scale covers your minimum and your maximum values when you're plotting, right? And now, question for you guys. What is my graph currently missing? What do I need to add to my graph before even calculating the gradient or anything? What are the elements that should be on your graph? Can you just open your mic and answer?
Sorry, need us.
I need a what?
Answer.
I'm not hearing you. Speak a little bit slower for me.
Your scale?
My scale, right? That's correct. So I need to put my scale on the graph, right? So next person, what is something else that's missing from my graph?
Title, sir.
Title, that's correct. Is there anything else that is missing from my graph? Or if I add the title and the scale, my graph is good. Just those. All right. So you're right, we do need to add our title and our scale. When you're selecting a scale, please choose an appropriate scale. On my graph here, I would have plotted up to 400 seconds, right? And if it is that you have 20 lines that you can plot on your x-axis, right? And you want to cover your graph, then I would suggest that 1 centimeter to 20 units is a fairly reasonable scale. Now, you want to ensure that your graph takes up roughly about 75% of your graph paper. So the graph should not be squeezed into a little corner. and it should not be stretched out too much. Now, I'll come to your question shortly, Aviva. Now, there's one thing that I'd like to add before I told you guys that you should always ensure that your maximum value is covered, and I said that you should read the question before plotting it. Now, the example that I'd use was if temperature was at like 65 degrees Celsius, right? Now, if you got a question and they said what temperature would be recorded after 1,000 seconds, it would be very impractical for you to try and plot 1,000 seconds on the graph, because that would reduce the actual points that you want to see. You'd reduce the graph too much. And so a question like that, you'd usually have to answer that by calculation and not showing the values on your graph. So if the values are too far out, as I said, if CSEC asks you for a specific value and it's too far out from your graph, that one has to be calculated. Don't bother try plotting that. Can go ahead with your question, Aviva.
Sir, I struggle sometimes with the scaling circles. Don't know. Do you have any tips that I can use for when I'm
When you're
trying
doing
to
your
find?
scale?
Yeah. Yes, sir.
Pretty much what I said before. Try to think about your maximum value and your minimum values, right? So 400 can easily be divided into 20 even spaces, right? Two, you want to avoid using complicated or awkward scales. For example, 1 centimeter to 3 units. That's a very awkward scale, and I'll explain why. So you'd usually use the major lines, which would be at 1 centimeter. So that's every 3 units. So your graph, the bottom of your scale would read, for example, 0, 3, 6, 9, 12, 15, and so forth for the major lines. But when it comes to using the minor lines for that scale, it becomes very difficult, right? There are 5 even spaces between your first major line, and so you have to divide 3 into 5 even spaces right there. That's 0.6. But if I told you to plot, for example, 2, right? It becomes very difficult to plot a value of 2, right? And so it's really on a case-by-case basis that you have to analyze it, Aviva. There are just going to be some cases where using, I say, a scale of 1 to 3 units is going to be impractical, and it's going to be very difficult to plot. You're going to have to guess where most of your points are. But in some cases, using that might be optimal. For example, if you're given a table and you notice that almost all the values are evenly divisible by 3, then yes, that would be a suitable scale to use on your x-axis. So it's just something that comes with practice, and you have to bear in mind the points that you need to plot and how difficult it's going to be to plot those points, right? So it's just something that comes with practice. I hope that answered your question. So we're going to be moving on to calculating our gradient now. Now, gradient is going to be our change in y values divided by our change in x values. Or you can easily say gradient is equal to rise over run, rise being vertical, run being horizontal, right? Now, when it is that you're selecting points to do your gradient calculation, I always tell people to choose the easiest pair of points that they can find. On this graph, I've selected 3 points. So 0, 25.086, 100, 33.896, and 350, 55.921. Out of those 3 points, I would definitely use the first point, which is 0.25.086, because 0 is a very easy number to work with. It's small, and whatever you subtract, if you have a number and you subtract 0, you always end up with that number. So it makes the computation very easy. Again, try to pick points that lie on major lines, so you don't have to be guessing, is that 0.86 or is that 0.85 or is that 0.9, right? Try to pick values that cut your graph line on major lines. Major lines being the bright vertical and horizontal lines. And again, it's just a matter of preference, which point you select as 0.2 and which point you select as x1, right? So I chose the more difficult values to use in this case, but as I said, you could have easily used 0.25.086. Would have made your work easier for you. Right? And so y2, which would be the y value from my 0.2, so 55.921 degrees Celsius, and you're going to subtract 33.896 degrees Celsius from that, right? And then for x values, remember to mute your mics and to turn off your videos when you're joining. So then you have 350 seconds less 100 seconds. Simple subtraction gives us 22.025 degrees Celsius divided by 250 seconds, or 0.0881 degrees Celsius per second. Now, when you're actually plotting your graph on the graph paper, you might not get the same gradient as me, but it should be pretty close to that value, especially if you choose a very good best fit line, right? So maybe your gradient is going to be 0.9, maybe it's going to be 0.7, maybe it's 0.85, right? You want it within that region. And I'm just rewriting the same gradient here, but I'm just changing the convention or it's being written. Now, found the gradient of our graph, and they asked us to determine the specific heat capacity using that gradient, right? And before we actually do the computations, I'm going to show you guys how is it that they determined that our gradient would be equal to P divided by the product of MC, right? There's just a bit of transposition here, and I would have changed the delta theta to theta at time t minus theta at time 0, or the initial temperature. So that's going to give you a change in temperature, right? Best fit line right there cuts the y-axis at 25.086 degrees Celsius. So I'm going to substitute that in. So that's our initial temperature. And transpose to get that equation. So theta t is equal to P divided by MC multiplied by T plus 25.086. That is the equation of our line. It's not necessary for us to do this in the actual exam because they told us that gradient is equal to P divided by MC, but I'm just showing you guys so you have a contextual understanding of how they got that, right? So question told us that the power was 105 watts and the mass of the liquid was 300 grams. So now we're just going to substitute and transpose. But before that, we're going to convert the 300 grams to kilogram to get everything in their standard units, right? And so our specific heat capacity is going to be equal to 150 watts divided by 0.3 kilograms multiplied by 0.081 degrees Celsius per second, right? Oh, I didn't actually state the value there. Let me just go. All right. Somebody put that in their calculator for me and tell me what they get. I inadvertently left out that line. So someone do 105 divided by 0.3 divided by 0.881. Tell me the answer that you got. Anyone got the answers yet?
$30.84.
You said 30.84?
Yes, sir.
And try that again. When you put it in your calculator, put the 0.3 multiplied by 0.881 in a bracket.
Oh, my bad. 3,972.76.
Right. That's what I got. I just calculated myself, and that is correct. So let's look back at the table of values that they gave us. Right? And so when you look at that table of values, the substance that is closest to the specific heat capacity that we calculated was milk. Right? Quick question. Anyone knows the specific heat capacity of water?
4,200 joules per kilogram per Kelvin.
Repeat that for me.
4,200 joules per kilogram per Kelvin.
Yeah, that's correct. So 4,200 joules per kilogram per Kelvin, or joules per kilogram per degree Celsius. So that's correct. You guys need to know that value. The question doesn't necessarily have to give you it, but they expect that you should know that value. And sometimes that question is asked on the multiple choice paper. Right? So 3,972.76 was our answer. And I need to put that in before I send you guys the slides. So just someone make a note of that and remind me at the end of the session. Next part of the question says, figure 3 shows a wind turbine used in some Caribbean countries as an alternative energy source. Describe how a wind turbine produces electrical energy. So in essence, when the wind blows, it causes the blades of the turbine to spin, right? They're shaped in a specific manner. And so as wind passes over the blades, it causes them to spin. And that mechanical or spinning, the mechanical energy or that spinning motion produces electricity. And so the blades are usually connected to some form of battery that stores the electrical energy that is produced. Right, now this is a question for you guys. State 2 advantages and 2 disadvantages of using wind turbines in some Caribbean countries I want one person to give me one advantage and one disadvantage, and then the second person to give me another one. So go ahead. You guys can put your answers in the chat, or you can open your mics and speak. I prefer if you speak.
So would an advantage be that it's a cleaner form of energy?
Yes, it's a cleaner form of energy. That's correct. What's a disadvantage? I mean, technically, it's very unlikely that they'll pretty much anything that you say, once it makes sense, you're going to get the mark. Right. So somebody says that it takes up space. Someone else says that it's ugly and it lacks aesthetic appeal. So we got two disadvantages there. Right. So somebody want to give me one more advantage. Right. Noisy, I guess. Yeah. Maybe expensive to install. Yeah, that's correct. As you said, you need a lot of land space, and land is very expensive. But one thing that you guys have failed to connect is the part of the question that says, in some Caribbean countries, right? No, you guys have to remember that Caribbean countries are very small and they don't have a lot of land space. So while you guys have said that it takes up a lot of land, to make your answer more complete, could just add the part that says that land space is limited in many Caribbean countries, right? Renewable, safe, or that should be disadvantages. Now, it's costly to set up, susceptible to hurricane damage. Again, you're linking this back to the Caribbean. It's a machine that relies on wind. Caribbean is very susceptible to hurricanes, right? And so they can become damaged. There's noise pollution as well. And as someone said, it lacks aesthetic appeal. And actually requires a large land space. So I hope somebody's making note of this. I need to change advantages to disadvantage. And number 5 should be requires a large land space. Right. Now C says that if the mass of air that passes through the circular area swept out by the turbine blades every second is 8.5 kilograms, and its kinetic energy during this time is 250 joules. We're to calculate the speed of the air and the input power of the air, right? So having read the question, we need to think about all the information that it's giving us, right? So the first useful bit of information is that it says every second. That tells you that time for this question is 1 second unless stated otherwise. Second thing, the mass of the air is 8.5 kilograms. Third thing is that kinetic energy is 250 joules. That's 3 useful pieces of information that they've given us, and we need to answer 2 questions based on those 3 things right there. Right? So speed of the air, we can use kinetic energy to determine the speed of an object. Remember, kinetic energy is the energy that an object or a body has because it is in motion. So kinetic energy is equal to half times mass multiplied by the square of velocity. So EK is equal to half mv squared. We need to find velocity. So the first thing we need to do, that we need to keep velocity on one side of the equation and everything else on the other, right? So when you're transposing, if you were previously multiplying by a half, when you transpose, you're going to multiply by 2, right? Or another way to say that is that if you were previously multiplying by a half, when you transpose, you need to divide by a half, and division by a half is the same thing as multiplication by 2. Now, mass was multiplying velocity there, so when we transpose, we're going to be dividing by mass. So we have 2 times kinetic energy divided by mass is equal to velocity squared, and we just find the square root of that if we need to find velocity. Now, having done that, now we're just going to plug in the values into our equation, and we get our answer. Now, you have 2 options here. It's either you're going to find what 2 multiplied by 2,500 divided by 8.5 kilograms is, and then find the square root. Or if you're going to do everything in one go, please ensure that that entire fraction is underneath the square root sign, right? So put it in a bracket if you have to ensure that you're calculating the correct thing. So you guys should get an answer of 24.25 meters per second. If you don't get this value, it's likely that you would have entered something incorrectly in your calculator. Just check again to see if you have all the brackets in the right places. Right. Now, input power. Now, given the question that we have on hand, calculating power is very easy. Power is equal to energy divided by time. The question told us that every second or per second, 250 joules of energy is produced, right? So 250 joules divided by 1 second is 2,500. Not 250 joules, but 2,500 joules divided by 1 second gives you 2,500 watts. Remember, watt is the same thing as joules per second. Right. And finally, we're to calculate the efficiency of the wind turbine, given that the output power of the generator is 1,350 watts. Now, the efficiency of any device, right, is going to be the output power divided by the input power, and then you multiply by 100. So 1,350 watts divided by 2,500 watts multiplied by 100 is going to give you 0.54%. Right. Now, if you ask me, I think that was pretty easy for a 3-mark question. Easy, easy, easy. Right. So before we go on to question 3, any questions? Remember, you guys can always put your questions in the chat. I'll check it periodically, or you guys can open your microphones and ask, or you can raise your hand and I'll see the notification and I'll get to you guys as quickly as possible. So I don't see any messages coming in the chat, so I assume that we're all good. So question 3 says that we're to state 2 properties of electromagnetic waves. And then part B says to describe how the cup and the string telephone works. Right, so guys, list some properties of electromagnetic waves for me.
They're all transverse waves and they travel at 3.0 times 10 to the 8th power in a vacuum or air.
Right, that's correct. Anyone else want to give me some more properties? So she said that they're transverse waves. Quick question before you go. What is a transverse wave?
A wave that has vibrations perpendicular to the direction of oscillation, like that, propagation.
Right, you understand what that means, right?
Yes, sir.
All right, you're correct. So one was that it's a transverse wave. The second property is that they all move at the speed of light, which is 3 times 10 to the 8 meters per second. Any other properties for electromagnetic waves, guys? I mean, one property is in the name. A property is that it has electrical and magnetic properties. I mean, it's in the name, a bit obvious, but you can still write that electromagnetic waves, they have electrical and magnetic properties. You can travel through a vacuum, as she rightfully said. Right. And so in this case, where they're talking on the string phone, what essentially happens is that when the boy speaks into his cup, the vibrations are the air molecules, they bounce on the cup, and they transmit those vibrations to the cup, which transmits those vibrations along the string towards the girl. When the vibration reaches the cup that the girl has, is going to produce the same vibrations that were originally caused those vibrations. And so you'll hear the sound system. Right? Remember to close your mics if you're not speaking or asking a question. Part 2 asks us to calculate the wavelength of the sound produced by the cup and string telephone, given that the frequency of the sound wave in ear is 11,000 hertz and the speed of sound in ear is 330 meters per second. Again, 330 meters per second is a value that you guys need to know as the speed of sound in ear, or speed of sound in ear. So you guys need to know that value. Not all questions will state it, so you need to know it. Right. Any ideas what equation we're going to be using to calculate this question?
V is equal to F lambda.
V is equal to F lambda. And what is lambda in this question? What does lambda stand for?
Wavelength.
Wavelength, that's correct. F is frequency and V is speed or velocity. Right? So it's simple, plug and chug, right? So 330 meters per second is equal to 11,000 hertz multiplied by lambda. Remember, hertz is the same exact thing as per second, right? So we just divide 330 meters per second by 11,000 hertz to get our wavelength, which is 0.027 meters, right? And if you wanted to convert that to millimeters, it'd be 27 millimeters, 2.7 centimeters. Question didn't ask us to do that, but we did so just the same. Give me a second, I'm going to backtrack to something quickly. Right. Back to this question here, question E. Now, we forgot to do one important thing. The question asks us to state our specific heat capacity of a liquid in one significant figure. Now, the answer that we calculated was 3,972.76. And so if you were going to state that to one significant figure, it would have to be 4,000, right? So I neglected to do that when we went through the question previously. Now, even though the question says one significant figure, you can't say that, oh, that means I should only have one digit in my answer and just put down 4 on the paper. That doesn't make any sense, right? So think of significant figures as a special kind of rounding off, in a sense, right? So you would ignore any leading to any following zeros. So 4,000, you'd ignore the zeros that follow the 4, and so that would be considered one significant figure, right? If it was 2 significant figures, you still have the same 4,000, and you would ignore the 2 zeros after 40. If it was 3 significant figures, still be the same 4,000. Wait, let me backtrack. Yeah, if it was 2 significant figures, it would still be 40, then you ignore the 2 zeros after that. If it was 3 significant figures, it would be 3,970, and you ignore that final 0. So even though it's 4, even though there are 4 digits, only the first 3 would be significant in that case. Yeah, back to question 3. I just remember that part of the instruction I were going through question 3. Right. So now we're going to be moving on to part C, I believe. This says figure 5 shows a coin at position O in an empty container. An observer is unable to see the coin based on the position of the eye, right? So in the diagram, the dotted lines shows the line of sight that someone needs to be in to see the coin. So because the eye, picture the eye right there, isn't on that broken line, the person cannot currently see the coin, right? So somebody looking from here would probably see something that's right here, right? So they won't be able to see anything that's at O or closer towards the side of the container. So the first question says to describe how the observer can see the coin when the container is filled with water. Anyone wants to tackle that question? All right, so I guess not. You guys are a little bit timid when it comes to this, right? Right. So in some aspect, it would be magnified, but it's not because of the magnification that we're able to see the coin. No, the coin wouldn't float to the top. It's a bit too heavy to float, right? But the reason we're able to see the coin because of the water is because water is going to refract the light ray, right? This is a refraction question, right? Where was that? Yeah. So see if I can find my part. Right. So let's say that water is in the container and water is at this level, right? But let me not use there. It's a bit difficult for me to explain at that height. Let's say that it's filled all the way up to the top of the container, right here, right? What essentially would happen is that light ray would travel from the coin up right here, and then because of refraction would bend this way and enter the person's eye. So let me use a different color for that. Let's use red. So the light ray would travel up here where it meets the boundary of water and air. Refraction is going to take place, and the light rays are going to bend and enter the person's eye that was right there, right? And so the water assists in that refraction process and bends the light rays towards the person's eyes. Now, one other tip for you guys, if it is that you're at a question and you're not sure how to answer it, what you could do is that you can look at the questions that follow it. Most times, CXE structures their questions in the same trend, right? So if they ask you a situation on refraction, they're going to give you refraction calculations afterwards. So if you can look at the calculations and determine that they are refraction-based calculations, it's very likely that the solution to the situation above is going to be based on the topic refraction. So that's something that you guys can look at in the exam as well. Similar, like if you're doing a multiple choice, sometimes you'll see one question, you don't know the answer. And when you reach down to another section, you see another question that is similar and it reminds you of the solution to the previous answer that you couldn't determine, right? So you'll see my formal answer shortly, but just to continue reading the question. So the refractive index of water is defined as the ratio of the speed of light in air, the speed of light in water. We're to calculate the speed of light in water, given that the speed of light in air is 3 times 10 to, I think that was 50 power meters per second, and refractive, no, that's probably 8, 3 times 10 to the 8, and the refractive index of water is 1.3, and then we're to calculate the critical angle of water, right? And so light rays, they travel in a straight line. However, when you pour water in the container, it causes the light, that should be light rays, bouncing off the coin to bend. And because air is less optically dense than water, the rays spread out more, and someone who was unable to see the coin before the water was added may be able to see the coin now, right? And so the second part of the question told us that the refractive index is equal to the ratio of the speeds in the different mediums, right? And so the refractive index of medium 2 relative to medium 1 is equal to the speed of the wave in medium 1 divided by the speed of the wave in medium 2, right? And the second line is essentially an expansion of the first. Many times we don't know the refractive index between two substances, like for example, glass and water. You don't know their direct refractive indexes. And so many times what we'll do is that we'll use relative refractive index. So you want to know the refractive index of medium 2 relative to air and the refractive index of medium 1 relative to air, right? And if you're referring to the refractive index of a substance relative to air, you don't need that subscript before the N. So our equation that we have here is V1 divided by V2 is equal to N2 divided by N1, right? And in this question, if we let medium 1 be air, right, this is what we're going to get. The velocity in air divided by the velocity in medium 2 is going to be equal to the refractive index of medium 2 divided by 1. If you're comparing the refractive index of a medium to air, right, then it goes without saying that the refractive index of air relative to air has to be 1. I think you guys should follow that level of reasoning, right? You don't expect that it is going to change, the speed is going to change if you're traveling from ear to ear, right? And so the refractive index of air by definition is 1. This was just some context right here. That section isn't actually necessary for the question that we're going to answer. Just some background for you guys. Now, to actually answer the question, they told us that the speed of light in air divided by the speed of light in water is equal to the refractive index of water relative to air. I need to fix that calculation. So it's 3 times 10 to the 8, not 4, divided by speed of light in water should be equal to 1.3. Right. So somebody put this in their calculator for me and tell me what the correct value should be. And depending on the calculator you're using, you might need to put the 3 times 10 to the 8 in brackets. All right, anyone want to give me the answer they have? 2.31 times 10 to the 8. Yeah, I'll work with that. It's a pretty long number, but I'll work with the 2 decimal places. Thank you. 2.31 times 10 to the 8. I'll fix that line later. Right. Remember, guys, just keep a note of all the corrections that I need to make to my slides and send me them at the end so that I can update them. Didn't get a chance to reread all the slides before session today, so there are probably a few more errors in there, but hopefully we'll identify all of them before the session ends and correct them as best as possible while we proceed. Right. So the only thing that I'll add to this slide here is just to say that refractive index, the full formula is that the sine of the angle of incidence divided by the sine of the angle of refraction is equal to refractive index of medium 2 divided by the refractive index of medium 1, which is also equal to the speed in medium 1 divided by the speed in medium 2, which is also equal to the wavelength in medium 1 divided by the wavelength in medium 2. I'll share the slides with you guys in the New Jamaica Foundation WhatsApp group after the session ends. Yeah. Right. So the next question asked us to determine the critical angle of water. But before we go ahead and calculate that value, we need to understand exactly what is going on. And so I'll start by asking you guys if you've ever heard of the term hydroplaning before, and it refers to cars. All right, thanks, Delmica. For persons that are in the session, do you guys know what the term hydroplaning means? Have you ever heard it before? All right, so hydroplaning is a phenomena that occurs on wet surfaces. Let's say that you're driving your car on the road and it's raining or there's a flood, right? If there is enough water between the wheels of the car and the surface of the road, it can cause the car to spin out of control, right? And the reason that occurs is because there's a difference in friction, right? So imagine you're walking in your house and all of a sudden you step on some oil, right? You're going to slip and fall, right? So it's pretty much the same thing that's happening here. Whenever light travels from one medium to another, there's a change of speed that occurs, and this results in a change of direction, right? Now, the change of direction only occurs whenever the light enters the second medium at an angle, right? So if you're driving an asphalt road and all of a sudden you drive onto a dirt road, right? And the two front wheels hit that dirt road at the same time, you will feel that decrease in speed, but you won't experience much of a change in direction, right? But let's say that you're going around a corner and half of the road is in asphalt, half of the road is in dirt, right? What happens is that one wheel will be on asphalt while the other is on dirt, right? And so it will cause that vehicle to have a sudden change in direction, right? So that's pretty much what's occurring here, the wave. Water is more optically dense than air, right? And so when light moves from water to air, it speeds up and there's a very drastic change in temperature. And so the rays spread out more than its initial angle, right? Now, the thing with critical angle is that if the rays spread out more than its initial angle, then there's going to come a point where that angle of refraction is 90 degrees and the ray is going to travel along the border of those two surfaces, right? And so that is critical angle. The critical angle is the angle that produces a refracted angle of 90 degrees in a less optically dense medium. So you won't have a critical angle going from air to water. That's because water is more dense, but you have a critical angle going from water to air, right? So the critical angle is the angle at which the refracted angle is 90 degrees, right? So sine C, or critical angle divided by sine of 90, is equal to N2, which is second medium, divided by N1. The sine of 90 degrees is 1, right? So we can just write that as sine C is equal to N2 divided by N1. Transposing that, that gives us C is equal to sine inverse of N2 divided by N1. Now, in this specific question, the second medium is air and the first medium is water. The refractive index of air relative to air is 1, right? So because the refractive index of air relative to air is 1, we can change NA to 1. So the critical angle is going to be equal to the sine inverse of open bracket 1 divided by NW close bracket. So sine inverse is equal to 1 divided by 1.3. 1 divided by 1.3 is 0.7692. And so our critical angle is 50.28. And if I'm not mistaken, I think the critical angle of glass is about 42.7 degrees thereabout. It might just be easier for you, Delmika, to just share the link to the group instead of adding everyone individually. Right. So, any questions? Are we good?
Good, sir.
All right. Let's try to see if I can get the link at the end. Oh, thank you. All right. It's currently 11:10. We're a bit behind schedule, but we'll proceed. right, I'm gonna ask if someone from the audience wants to read this question for me. All right, no one wants to read, so I guess I'll continue. All right. So draw a labeled diagram of the structure of a thermocouple thermometer. And two, the thermocouple thermometer is used to measure the temperature of the blue part of the flame of a small candle. State 3 reasons why a thermocouple thermometer is suitable for this application. So before we look at the diagram, what would you say are your 3 reasons why you would use a thermocouple to measure the blue part of the fire, right? What do you know about a thermocouple? How can you apply it to this question right here? Generally speaking, the thermometers that you're thinking about should be a laboratory thermometer, your clinical thermometer, and your thermocouple, right? So out of those 3 thermometers, they chose to use a thermocouple. And the question is asking you, why do you think that they chose to use the thermocouple? Right? Anyone wants to give an answer? Right. So someone said that the thermocouple has a high temperature range, right? That's a good reason. No, the only thing I'd add to that is that the blue part of the fire is going to be the hottest part. And so you need a high range on your thermometer to detect that temperature, right? All right, so Nikki says that it responds quickly to changes in temperature. Yeah, I like that. Joshua says it can be calibrated. No, I'm not sure if this is what he means, but I think he's trying to say that because the thermocouple is electrical in nature, you can connect it to electrical devices to get readings, right? That's what I think he's trying to say. So those are 3 solid reasons that you guys gave there. Right? So pretty much this is just a simple diagram. The essence is that the thermocouple is made from 2 different types of metallic wires. So it could be copper, it could be iron, whatever it is that you want, right? And because of that difference in conductivity between the wires, it's able to detect a change in voltage, right? So usually you want to have one junction where the 2 wires meet exposed to the hot element, and then you want to have another junction exposed to something that's cold. They usually use like ice, right? There's a pretty simple diagram here, nothing too technical. And reasons are, again, wide range, so we can measure extremely hot object, small junction, so you can put it in a place that's small and precise. Remember, the blue part of the flame is very small, right? So that's another. Responds quickly, absorbs minimal heat from the object that it's measuring, right? So those are 4 reasons why you could use a thermocouple in that circumstance, right? Question 4 says figure 6 shows a fixed mass of gas which is trapped in a cylinder by a piston. The gas is at atmospheric pressure 1 times 10 to the 5th pascals. The volume of the trapped gas is 1.9 times 10 to the negative 4 meters cubed, and the initial temperature is 27 degrees Celsius. An electrical heater is used to increase the temperature of the trapped gas to a final temperature of 627 degrees Celsius, and they've given us a diagram here. First question says to use the kinetic theory to explain how a gas exerts pressure on the piston. All right. So I'm posing this question to you guys. Using the kinetic theory, how does the gas exert pressure on the piston? Right? And you probably should start by first telling us how does a gas exert pressure. You can just open your mic. Someone step forward.
So sir,
Go ahead.
gas trapped in a container exerts pressure on its surroundings by hitting it at a specific velocity and frequency. So as heat is applied to the area where the gas is, energy is transferred to the molecules of gas as kinetic energy. This thereby increases the velocity of the particles trapped therein. And because it is in such a confined and enclosed space, the frequency and the frequency at which it hits the walls of the cylinder, as well as how hard it hits it because of the increasing velocity increases. So that will explain how pressure inside of the cylinder increases.
All right. That's good, Joshua. Anyone else want to try their hand at explaining it? I'm not saying that Joshua is wrong. I'm just want to hear from you guys. How Joshua explains how a gas exerts pressure might be different from how I explain it, might be different from how Gabriel or John or Mary explains it. So I want to hear how someone else explains how it is that a gas exerts pressure. Put it in your own words for me. Thanks, Joshua. Someone else? Come on, it's not that difficult. Anyone else want to try? All right, Brianna, do you want to explain, or Brianna, I'm not sure your name is pronounced. Do you want to explain how it is that gases exert pressure? All right. Anyone else? All right. Never mind. All right. I guess no one is brave enough to attempt it. Thanks, Joshua, but you're pretty much correct, right? And so before getting into the kinetic theory, we first have to ask ourselves how it is that a gas exerts pressure and what is pressure, right? So we'll start with force. Force is equal to mass multiplied by the change in velocity divided by time, and that's from Newton's second law, right? And so the particles inside of a container or gas molecules, they are in constant random motion. Random meaning in different directions, but they're usually at a constant velocity moving about, right? Now, when you have a gas trapped within a container, like an aerosol can, right? The air molecules are going to bounce on the sides of the container. In this case, there's a piston, And so the air molecules, they bounce on the piston and they create a force, right? So when they bounce, they're going to change direction, and that causes a change in velocity, right? So let's say, for example, it was traveling at 0.5 meters per second to the right. When it bounces off, now travels 0.5 meters per second to the left, or negative 0.5 meters per second to the left. That change in direction causes a force, right? And so this force acts on the surface of the piston, right? And so the gas is going to exert pressure on that piston. Remember, pressure is force divided by area. So we've explained how the gas created a force, and the area that that force is being applied to is on the piston, right? Now, if the gas particles are heated, as Joshua rightfully said, it's going to increase the kinetic energy of the particles, and so they're going to be traveling faster to and from the piston, right? And so this increased speed creates increased force, right? However, the contact area of that piston is going to remain the same, right? And so what you'll have is that you'll have an increase in force while surface area remains constant, and therefore pressure is going to increase, right? Now, the only thing that I would add to that, it's not exactly necessary for the kind of question that they asked, but if you look at the diagram, the piston is inside the container, and you see where they showed you two arrows pointing to the right, right? And so that what that tells us is that that piston is able to move freely, right? So as the pressure builds up and there's greater force on the surface of the piston, it's going to push the piston outside of that cylinder. And so the volume of the air trapped in that container is going to increase. Now, the reason I have these words highlighted here in yellow, right, is because that includes the addition of heat to the situation, right? If you were just describing the kinetic theory in general, right, there wouldn't be any need to mention the additional heat that is added to the system, right? Right, so Brenner says, as heat is applied to the gas, the particles absorb the kinetic energy and they begin to move randomly at a rapid pace, hitting the walls of the container. Right? That is absolutely correct. Thank you, Brianna. Oh, Brianna. I'm sorry for mispronouncing your name. So on to the next question. This question says to calculate the final volume of the gas given that the final pressure is 1.8 times 10 to the, I think that's 5 pascals. So now I'm asking you guys this question. What rule or what equation do you believe that we're going to use to solve this equation? Right? Are we going to use Charles' law, Boyle's law, pressure law? What law are we going to use? Are we going to use the kinetic energy formula? Are we going to use the force formula? Are we going to use pressure formula, what formula are we going to use to calculate this question? Right? So I have one person that says we're going to use a combined gas law. Someone else says that we're going to use Charles' law. All right. Anyone else wants to say what they think we're going to use, or are you in agreement? I want to know if you're in agreement with the combined gas law or Charles' law. If you want to propose another equation or law, I'm also fine with that. You can just put your answers in the chat, whether you agree to the combined gas law or Charles' law. Let's give you guys a few seconds to sleep. Come on, guys. I mean, it's just us here right now. Whether you're wrong or you're right doesn't change anything. No one is going to judge you for it. This is a learning session. If you're given this question to do on your exam next week, would you choose Charles' law or combined law? PXV. PV. All right.
Charles.
All right. So someone said Charles. All right. Anyone else? All right. Someone else agrees with the combined gas law, otherwise known as ideal gas law. All right. So we have 2-2 so far. Anyone else? All right. So I guess you guys are still undecided, but the correct answer is that this question would require you to use the combined gas law, right? Now, I know the question said to you guys that the final pressure is 1.8 times 10 to the 5th pascals, and you may be tempted to assume that they're trying to tell you that pressure is fixed, right? That's not the case, right? It's not the case. This question could have easily just said calculate the final volume of the gas, and then the part that says given the final pressure could have been stated in the initial prompt of the question, right? So how do you know that you need to use all three values or use ideal or combined law? Go back to the initial question, right? It says the atmospheric pressure is at 1 times 10 to the 5 pascals. So that's initially. The other question told you that it's final at 1.8. So we have an initial pressure, we have a final pressure, right? Next one says the volume of the trapped gas is 1.9 times 10 to the 4 meter cube, right? And they want us to determine the final volume. So we have an initial volume, we need to determine the final volume, right? And it says that the initial temperature is 27 degrees Celsius and the final temperature is 627 degrees Celsius. So in this question, all three values are moving, right? All three values are moving, so you have to use combined gas law, the ideal gas law. The second thing, right, is that if it is that we were going to fix the pressure of the system so that it did not move, right? They wouldn't need to tell you that the final pressure is 1.8, right? They could have just completely ignored that line whatsoever. If that part, if that statement was not a part of the question, then you would use Charles' law. But because they gave you an initial pressure and the final pressure, it means that the value was changing, right? And the third reason is that if you wanted to fix pressure in this kind of an experiment, Let me see. Wanted to fix pressure. No, you can't trap it. Yeah. Essentially, what would have to happen is that the walls of the entire system would have to expand proportionally to the force, right? So as the particles speed up and there's increased force, right? Not only the piston would have to move, but the cylinder itself would have to expand as well, right? So you'd need the entire container and not just one side to expand uniformly. Because remember, the pressure isn't just acting on the piston, the pressure is also acting on the walls of the cylinder, right? So force is exerted on the piston, the force is also exerted on the walls of the container. And so to keep pressure fixed, you'd have to have it expand uniformly. So you can think about it like a balloon in a sense, right? So like the balloon where it can freely expand in all directions. You need a similar setup if you wanted to fix the pressure. Right? But getting back to the point, you have to use a combined gas law for this question. Right? And so we have pressure 1 multiplied by volume 1 divided by temperature 1 must be equal to pressure 2 multiplied by volume 2 divided by temperature 2. And before using this equation, you have to change temperature from degrees Celsius to Kelvin. Pressure and volume can be in any units, but temperature must be in Kelvin. So pressure could have been in atmosphere, could have been in pascals, could have been in bars. Doesn't matter. Volume could be in meter cube, centimeter cube, it could be in liters. Doesn't matter. But temperature has to be in kelvins, right? Now, remember to change from Celsius to Kelvin, or they have to just add 273. So we get 1 times 10 to the 5 pascals multiplied by 1.9 times 10 to the negative 4 meter cube divided by 300 Kelvin is equal to 1.8 times 10 to the 5th pascals multiplied by our unknown volume divided by 900 Kelvin, and transpose, right? Right there, I just changed the exponents to make it a bit easier for us to follow visually, right? And we transpose and we simplify, put those numbers in our calculator. Again, depending on the calculator that you're using, you might need to put the 300 times 180,000 in a bracket, right? So if you're using division sign, ensure that those two numbers are in a bracket. If your calculator has the fraction button, then you don't necessarily need to put in a bracket. Just make sure that everything is in the denominator and the rest is in the numerator. And so our final volume is 0.003167 meter cube, or 3.167 times 10 to the negative 4 meter cube. That is the end of question 4. Question 5 is logic gates. Now, logic gates is a pretty simple topic. It's not difficult at all. Some persons still have challenges with it, but it's not difficult. I think of it as 3 marks, right? Now, when you look at this image right here, and they ask you to identify the logic gate, this gate is the NAND gate. And it's pretty much just recall, right? They normally provide you guys with a table in class, not in the exam, right? And you just need to sort or study what those gates look like and their truth tables, right? Now, the NAND gate resembles an AND gate. However, the small circle at the end indicates that you're going to NOT it, right? So the NAND gate is the NOT AND gate. So it's and then you NOT the result. And the only truth table that only has 2 rows is going to be your NOT gate or your inverter gate, which says any input you give me, I'm going to give you the opposite. So if you give me 0, I'm going to give you 1. And just as a point of note, 0, off, or false, they all mean the same thing in logic gates. 1, or on, or true, or high, all mean the same thing. So 0, off, low, or false, they're all the same. 1, on, high, or true, all the same thing, right? All right. And now they've given us a circuit and they want us to determine the output, which is Z. So I want you guys to help me to identify the logic gates that are in our circuit, right? So I'm going to start with the gate at the top. Which one is that? The one that produces output C. Which gate is that? OR gate, all right? The one that produces output D, as in dog, which gate is that? That's not gate, that's correct. The one that produces E, which is the one that we saw before, we know what that's our NAND gate. And the one that produces output Z is the exact same as the one that produces output C. So that's also an OR gate, right? Right. So let's do our truth table now, right? Now, one point to note is that there are 2 inputs to this system, which are A and B, and therefore we're going to have 4 possible combinations, right? So 2 to the n, where n is the number of inputs. So we're going to get 4 possible combinations or 4 rows to our table. If there was a 3rd input, we would have 8 rows to our table, right? All right, so we said before that C is the result of our OR gate, right? And the OR gate says that once I have one input that is true, then I will produce a true output. So C is the OR of A and B. So C is A or B. And so the result is going to be 0, 1, 1, 1, right? D or not B, right? Remember, the NOT gate says any input I get, I'll give you the opposite, right? And so anywhere we have a 0 in column B, we're going to put a 1. And anywhere we have a 1 in column B, we're going to put a 0. So that's going to be our output at D, right? So D is just not B. E is C NAND D. So the NAND gate is the NOT AND gate, right? So a regular AND gate says, once all inputs are true, I will produce a result of true. So if you NOT the result, what it says is that once all inputs are true, I will produce an output of false, right? Wait, what? Right? Yeah. So E is C NAND D. The only case where both inputs C and D are true is in our third row. So on the column E in the third row, we're going to put a 0, and then everywhere else we put a 1. And then finally, output Z is going to be C or E. And remember, the OR gate says, as long as one input is true, I will produce a result of true. When you look at C and D, there's a 1 in every C and E, sorry, there's a 1 in every single row. And so the output will always be true, right? So you will never get an output of false for this system. I mean, it's possible you can design just about anything that you want with a logic gate. I personally don't see the use of a circuit that always produces an output of true, or it's always on. I don't know, right? Well, there must be some use for it. I guess probably like a security system. You never want the security system to be off. You always want it to be on, right? So I guess it would be useful in that case. If you never, if for example your two inputs are the front door and the back door of your house, right? You'd always want the alarm to be engaged but not ringing, right? That's probably not the best example. I'm trying to think what situation would be ideal where you're always getting a constant output of on. I can think of where it would be useful for the system, the alarm system, to be on always, but I don't see where it'd be useful for the alarm system to be ringing constantly, if you get what I'm trying to say. But either way, if you double check the table, it still produces 1 in every single circumstance. So we're not going to waste any time or any brain cells trying to figure out why they gave us this. We just accept it as what they wanted us to do, and we move on with our day. But that's good. That, you know, as you rightfully said, it's very unusual for them to give us a circuit that's always produces a high output. And so you might be tempted to think that something is wrong with your truth table. You just look back over it quickly, and if you can't see anything to change or any reason why you might have got the wrong answer, you leave it alone and you move on. Now, B says, figure 9 shows an arrangement for an electromagnet. State a material which is suitable for the core of the electromagnet. Now, easily, that's going to be iron, right? easily. 1 mark there. List 2 factors which would cause an increase in the strength of the electromagnet. I'm going to pose that question to you guys. Right, so Brenner says to increase the number of turns of the coil. Yes, you can do that. Someone else give me another way or we can increase the strength of the electromagnet. I can think of at least 2. I mean, remember in this case, you're creating the electromagnet. So using a stronger magnet wouldn't be an ideal answer for this setup. But think about the other elements that are currently in your circuit, right? So somebody says to increase electricity, same thing as increasing the voltage, right? So you add more batteries to your cells. So instead of 12 volts, maybe you increase it to 20 volts. That is again going to increase the strength of the electromagnet. Now, can anyone think of a third way to increase the strength of the electromagnet? Again, you want to look at the components in your circuit. Bigger wires, no, I don't think so. Yeah, Joshua, manipulating the resistance, right? Now, if you decrease the resistance of the circuit, it means that there's going to be a greater current that it's flowing, right? So even if I use the same 12 volts battery, to decrease the resistance in the circuit, you're supplying more current, and that's going to create a stronger electromagnet. So our 3 methods would be, yeah, you are right, increasing the wires. Increasing the wires does reduce the resistance in the system, but I don't think that's an optimal answer for this question. Like, for example, you wouldn't expect them to go and get wires the size of cables, like the one that run on the light posts outside. You wouldn't expect them to go and get wires that size for this kind of an experiment, right? And so, yes, we could use bigger wires to reduce the resistance, but it's not going to be as drastic with the wire sizes that we would use, right? There's going to be some reduction, I'm not denying it, right? But it would be much easier for us just to change the resistance. It's a variable resistor, so we can change the resistance easily, or we can switch it out for a fixed resistor for a lower value. That's much easier than trying to find a thicker wire for us to use. And part 3, which said state how component X can be used to increase the strength of electromagnet, we basically identified that already. Right, and now it says that the switch is closed. The reading on the ammeter is 1.5 amps, and we're to calculate the resistance of the circuit. Simple. Ohm's law. Volts is equal to current time resistance, right? V is equal to IR. We know that the voltage or EMF of our battery is 12 volts. The reading on the ammeter is 1.5 amps. Transpose, and we get our resistance of 8 ohms. And then the final question for the 2023 paper says, figure 10 shows a vacuum tube with a radioactive source which emits alpha particles, beta particles, and gamma rays through an electric field. were to describe the paths of the alpha particles, beta particles, and gamma rays as they pass through the electric field, right? And we're to give a reason, right? So I want 3 persons to answer, 1 person to say what's going to happen to the alpha particles, another person to say what's going to happen to the beta particles, 3rd person to say what's going to happen to the gamma particles. And remember to state your answer. It's a 2-mark question. So you just state what happens, why, 2 marks. Right. So someone says that beta particles are going to be deflected to the positive side. All right, so why is it going to be deflected to the positive side? All right, someone says the gamma rays will pass through undeviated through the vacuum. Right, they pass through undeviated. Yes, that's correct. But why does it pass through undeviated? You guys are giving away marks there. Remember, the question said to state what happens and why. Right? State the reason. Right. And someone said that the alpha particles are going to be deflected from the positive side to the negative. And his reason is because alpha particles are positively charged, right? There's something that's missing from your answer, Joshua. So think about it, I'll get back to you shortly. Right, so the gamma rays pass through undeviated because they have no charge. That is correct. The beta particles are negative, right? And so they attract to the positive side. And that is correct, right? So it's not that what you stated is incorrect. I just think that you need to add a bit more information to that. And I'll tell you guys why. Now, what you could add is that the alpha particles are weakly deflected towards the negative pole or negative terminal. And that's 2 reasons, right? 1, they're positively charged, so they're attracted to the negative plates. And 2, they are heavy, right? Alpha particles, they have protons, neutrons, right, in the nucleus. And so it's heavier than an electron or a beta particle. The beta particle is going to be strongly deflected to the positive terminal. And again, that's because they're light and they're negatively charged, right? So that's it. So don't give up any marks there, guys. And then part B says the equation below represents one nuclear fission reaction utilized in power plants, right? And they've given us the equation and they've given us the masses of each element. And they said to calculate the total mass of the particles, left-hand side, and the products, right-hand side, right? Now, we're doing simple addition here. Total masses, you're just adding the masses. So the masses, total mass of the particles, is going to be the mass of U-235 plus the mass of the neutron. So we're going to have 3.902 times 10 to the negative 25 kilograms plus 1.675 times 10 to the negative 27 kilograms. And so the total mass of the particles is going to be 3.91875 times 10 to the negative 25 kilograms, right? Now the total mass of the products is equal to the mass of barium 141, krypton 92, and 3 neutrons, right? So 2.289 times 10 to the negative 27 kilograms plus 1.575 times 10 to the negative 7 kilograms plus 3 multiplied by 1.675 times 10 to the negative 27 kilograms. And that gives us 8.889 times 10 to the negative 27 kilograms, right? So before going further, I have 2 questions for you guys. One, have you done the 2023 paper before? And 2, does anything look wrong with this question to you guys? Or the question is good how it is? And if you say that something is wrong, I'm going to ask you to tell me what you think is wrong. So is the question all right? Right. So is there a problem with this question, or is the question good? Now, the fact that you did the paper before doesn't really affect you, right? Because if there's an error in a question that CSEC gave you, then they can't penalize you for anything, right? So you said the question is correct, or it is, right? Someone says, I haven't done the question before, but nothing looks wrong. Anyone else want to give their opinion whether they think something is wrong? All right. All right. So what I will say is that there is an error in this question, and I want you guys just to stop for a minute and look, right? Let's look at the mass of U-235, which is 3.902 times 10 to the negative 25, right? That's 10 to the negative 25. The mass of a neutron, 1.675 times 10 to the negative 27. So that's to the negative 27 power. Now, let's look at the mass of let's look at the mass of krypton, right? 1.575 times 10 to the negative 27 power. So we have U-235, a mass to the power of negative 25. We have Kr-92, which is a mass of negative 27 to the power of negative 27. And we have the mass of a neutron, which has a power of 10 to the negative 27, right? Now, a neutron, one single neutron, 1.675 times 10 to the negative 27. Based on this question, it weighs more than an atom of krypton, right? With 36 protons and a total mass number of 92, right? So how is it that one neutron is heavier than an entire atom? Something is adding up there, right? And so there is an error in this question. But as I said, even if you didn't recognize the error and you work the question with the values that they gave you on the paper, they cannot penalize you, right? Because they would have given you incorrect values to use, right? And so I believe that what they should have done is that for barium and krypton, it shouldn't have been to the negative 27 power. I believe it should have been to the negative 25th power, right? And if we go with that assumption, the total mass of the products is going to be 3.91425 times 10 to the negative 25 kilograms, right? Which is pretty comparable to the mass that we had for our particles side, right? Now, there is no reaction, nuclear reaction that you're going to do where there's going to be a significant reduction in mass, right? So it's not going to go from times 10 to the negative 25 to times 10 to the negative 27 in the reaction. Some of the mass is used to produce energy, but it's not going to take that much mass, right? And just for added clarity, these questions are from the 2017 and 2022 CSEC paper, right? You look at the values here, in the 2017 one, everything is expressed to times 10 to the negative 27. But krypton is 152.6, while the neutron is 1.670, right? And if you look at the 2022 paper, where they express mass in atomic mass units, the neutron was 1.009, while krypton was 89.847, right? And so there definitely was an error within that question. And even though the atoms in these questions aren't the exact same ones that was in our question, you don't expect that isotopes are going to have wildly different masses, right? Masses are going to be comparable to each other. So maybe one has a mass of 152, while the other one has a mass of 151. Something that's pretty close, right? So we'll continue with our question. Damani, if you're not hearing anything, just leave and rejoin. Hopefully the audio will sort itself out. Somebody just put it in the chat for him if he hasn't already done so, right? So the mass difference is just a difference in mass, and then afterwards it asks us to calculate the energy that's released from this reaction, right? So if you had used the incorrect values, right, the mass difference that you would have got would have been 3.82986 times 10 to the negative 25 kilograms, right? And then we're going to use Einstein's equation. E is equal to mc squared to determine the energy that would have been produced by that change in mass. Right? Remember, this is going to be 3 times 10 to the 8 meters per second squared. And when you're squaring that value, you're going to get 9 times 10 to the 16. So 3 squared is 9. 10 to the 8th power squared is 10 to the 16, right? And so we would get 3.4 times 10 to the negative 8 joules for our answer if we use incorrect values. Right? Now, if we attempted to use correct or assumed values, right? Our mass difference would have been 4.5 times 10 to the negative 28 kilograms, which is less than 1 neutron, right? And when we use Einstein's equation, we get 4.05 times 10 to the negative 11 joules. Now, I honestly can't tell you if it is that you come across a question in the exam whether to use incorrect values or to use the values that you assume. Right? I can't tell you which one to use definitively. What I'll say is that if you use the incorrect values, then they shouldn't penalize you because those were the values that they gave you, right? No, if you're going to assume a correction, right, then you need to state it, right? So you need to tell them why you believe there's an error in the question, and you need to state the correction that you have been making, right? But if it's that you do that and the question was correct to begin with, then you forfeited those marks. You forfeited some of those marks because you still get marks for using the correct equation and the principles, but you wouldn't get all the marks. So out of the two, the safer bet is probably just to use incorrect values and probably add a note to say that you believe that the question was incorrect. However, you're still using the values that were given. That would probably be the best course of action. All right. So before we continue, any questions? Any questions on the 2023 paper before we moved on to selected questions from some other years? I take it that everyone understands and we're all good to go. All right. So moving on. Probably not going to finish at 1 o'clock, but you'll see how best you can do. Try to cover as much questions as possible. Now, this question is from the 2017 paper. This was the year that I did the exam, and to be honest with you, I'm still not 100% sure what CXE wanted for this graph. I need to go back and check and see if I can find the exam report for this year and read that. All right, but I'll explain why I'm not so sure what they wanted shortly. So it says an experiment in which a magnet was allowed to fall through a coil was conducted to test the concept of an induced EMF. The voltages were recorded at different time intervals using a scale of 2 centimeters to 5 milliseconds on the horizontal axis and 2 centimeters to 0.5 volts on the vertical axis. Plot the graph of induced EMF, voltage V versus time ms on the grid paper provided. So in this question, they've given you the scale to use. Please ensure that you use that scale that they're giving you. My graphs may not be to the same scale, but the principles should still apply, right? It says to use the graph to determine the induced EMF after 12.5 milliseconds, right? Based on our table, 12.5 is within our range of values, right? So we're good there. And then B, the time in milliseconds other than at the beginning of the experiment when the induced EMF was at 0 volts, right? Now, when I did the exam, many persons use a straight line to connect the points, like the graph on your left, right? And some persons use piecewise best fit lines, right? Like the graph on your right. However, these two graphs are incorrect, and that's because voltage is a wave, so it's not a straight line graph, right? Now, depending on how you draw your curve, right, you're going to have different readings for your values, right? And so one person might draw their curve a bit steeper than the other, and so you can get varying degrees of answers when you read your value at 12.5, right? So if you try to read the value at 12.5 for these two graphs, the graph that is in green is going to give you an answer of 1.5, but the graph that is in red is going to give you an answer of about 1.8, 1.9 thereabout, right? And if you're looking for the value where it cuts the x-axis, you're going to get an answer of about 27 if you use a red graph and about 28 if you use green one, right? These would have been like best fit curves. That's how you're going to get varying answers. Now, if you try to connect all the points using a curve and not a straight line, then this is more or less what you'd get. you'd get 1.5 volts for the voltage at 12.5 seconds, and your value when the EMF is at 0 is going to be at around 27.8, right? So I'm really not sure whether or not they wanted to use a curve that connects all the points or a best fit curve, but you should get relatively similar answers depending on which one you use. Again, I said I'll try and see if I can find the subject report for 2017 and see if they gave instructions for this question. Right. So now on to the next part of the question. It says, Kevin, a physics student, conducted an experiment, determined the effect of electromagnetic induction, and he used the following apparatus, right? The magnet is pushed into the coil, the north pole entering first, and we're to draw on the diagram the direction of the induced current and the direction of the arrow and the galvanometer as a result of this motion, right? Now, things to note is that Lenz's law says that the induced current always flows in the direction that opposes the motion that creates it, right? Now, you could use the right-hand grip rule, but you have to apply Lenz's law to it after that, right? Now, usually, when you're referring to a coil, current exits the north side of the coil, right? But because we're inducing current in this circumstance, current is going to enter into the north side of the coil, and we'll identify which side of the coil is the north versus the south shortly, right? Now, another thing to note is that this setup right here, there is no battery. There is no cell in the setup. So there is no current that is flowing into the system initially, right? It's because we're moving the magnet in and out of those coils that a current is generated or induced, right? So if the magnet is removed from the system, there should be no current flowing any at all. So this diagram right here, it just shows you under general circumstances that current leaves the north side of a coil. And remember, this is not for induced current. If it was induced current, the current would be entering the north side of the coil. These are my directions that gonna get the current flowing, and explanation is coming shortly, right? So let's imagine our experiment where can you look at my diagram here? We're going to try and determine what side of the coil is the north side and what side of the coil is the south side. And then from there, we will determine the direction of the current, right? So remember, a magnet, the magnetic flux are the field lines, they flow out from the North Pole and into the South Pole, right? Now the coil in our system, we don't know which side is north or south as yet, and so we need to determine that. But remember, it's always in such a way that it opposes the field lines that are trying to enter the coil. Now, as we push the magnet into the coil, you're going to have field lines, magnetic field lines, cutting our coil, right? So magnetic flux lines are going to be trying to enter the coil. If it is that the side of the coil closest to the magnet is the south pole of our coil, then there's going to be no opposition because the magnetic flux lines are going to leave the north side of the magnet and they're going to flow into the south side of our coil. So there's no opposition taking place in that sense, right? Now, if it is that the north side of our coil is closest to the magnet, there is going to be some degree of opposition. Remember, magnetic field lines, right? They never cross each other, and north to south, they try to avoid each other, right? So the magnetic field lines that are exiting the north side of our magnet, they're going to be fighting against the magnetic field lines that are generated from the north side of our coils. They're going to be opposing each other, right? And because of that, we can identify that our coil has the north side closest to the magnet. And remember, current enters on the north side of the magnet. Induced current enters the north side of the magnet. Right. So we've just identified that our north is here and our south is here. And remember, current enters into the north side. Induced current enters into the north side, right? So current is going to flow in this direction. Clear on that? All right, so I can move on to the other part of the question. All right. It says explain why an induced current is produced. Now, as we said, as the magnet is moved towards the coil, more magnetic field lines from the magnet are cut, and this induces current in the coil. Why is it necessary to use a sensitive galvanometer? So that we can detect small changes in the induced current. Now, if it is that the magnet is now being pulled away from the coil, what's going to happen is that our current is going to flow in the opposite direction, right? So now it's going to be flowing from left to right. Remember, induced current is in the opposite direction as the motion that creates it, right? So when we were putting the magnet into the coil, current was flowing towards the north side of the coil, right? Now that we're removing the magnet, right? And part B says that we're to state 3 changes or adjustments that Kevin could make to increase the induced EMF. So I pose that question to you guys. You were conducting the experiment. How would you increase the induced EMF, right? What things can you change to increase the voltage or the current that is produced? right? So I'll start with the first thing. Well, the first thing, all right, so someone said that we can increase the turns of the coil. That's true. My answer is that we can increase the speed that we move the magnet, right? So if the magnet is moving faster, the induced current is going to be stronger. And the third thing that we can change is the magnet, as someone said, right? You can just use a stronger magnet. So those three things will cause an increased voltage or current. Speed of the magnet, the strength of the magnet, and the number of turns or coils. And again, if the magnet is stationary within the coil or it's not moving outside of the coil, no current is going to be produced, right? The induced current is produced because of the motion or the movement of the magnet. This is 2017's paper. We're not doing every question on 2017. We're just looking at a few select questions from different papers. I think we'll also look at question 6 from the 2017 paper. There's a question on 2018. Our next question on 2022 that I want to look at. And part D now, they've given us an AC generator and they've told us that the coil PQRS is connected to the other components of the circuit, which allow the coil to rotate in the direction indicated by the arrow. If you look on the diagram, the arrow is in a clockwise direction. The only thing that I would change with the wording of this question, instead of saying PQRS, I would say PSRQ. Just for ease of reference, I would prefer to call it that way, but it doesn't matter. Either way, we look at it. So it says that we're to draw on figure 3 the direction of the induced current if the coil rotates in a clockwise direction. Now, I know that you guys have been taught Fleming's left-hand rule. Now, Fleming's left-hand rule only works on a current that is generated from a battery. If you're referring to induced current, you have to use Fleming's right-hand rule, right? Which is essentially the mirror of Fleming's left-hand rule, or it's Fleming's left-hand rule plus Lenz's law. So remember, Lenz's law says that induced current flows in the opposite direction to the motion creating it, right? So if you add that to Fleming's left-hand rule, you get Fleming's right-hand rule. And the fingers still mean the same thing. The thumb shows the direction of the force, right? The first finger shows the direction of the magnetic field, and the third finger shows the direction of the induced current, right? I'll get back to the direction shortly. Just answer the other parts of the question, which asks for the period if the rotation is 0.02. If the coil rotates 0.02 seconds, we're to calculate frequency. Now, frequency is just 1 divided by period, or its inverse. So 1 divided by 0.02 seconds is going to give us 50 per second. So this coil is going to rotate 50 times in a second. Fleming's right-hand rule, as I said, it's Fleming's left-hand rule plus Lenz's law. And the direction of the induced current is going to be from P to S and from R to Q. So it would follow PSRQ. So on the side PS, current is going away from us. On the side RQ, current is coming towards us. Whenever you're given AC or DC questions, you want to think of your perspective as in front of these two rings right here, right? So essentially, you want to think of it like this. So you're seeing the wires and the north and the magnet, right? So you have the north side of the magnet, south side of the magnet. Magnet with the X suggests that current is going into the plane of the paper or away from us, right? And current is coming towards us. That's what the dot represents. Current is coming towards us or it's coming out of the plane of the paper, right? So applying Fleming's right-hand rule, first thing that you need to do is identify the direction of the magnetic field. Magnetic field always goes from north to south, right? So start with Fleming's left-hand rule, put your 3 fingers so that they're perpendicular to each other, right? So the thumb point up, your index finger towards your laptop, your phone, your screen, whatever, and your middle finger pointing to whatever direction that it's pointing to the right hand, right? Now, we haven't applied Fleming's left-hand rule as yet, right-hand rule, and now we're going to do it, right? So you just want to get your hand in the proper position first before you apply the rule. So your thumb up, your first finger pointing towards your laptop screen or your phone screen, whatever you're viewing, and your middle finger should be pointing towards your left. Remember, you're using your right hand to do this. Physics at the atom, we did that question 6 on the 2023 paper, where we talked about alpha particles, beta particles, gamma particles, and the nuclear fission equation. That was the atom of the physics. Sorry, physics of the atom. But back to this question now. After we have our hand in the correct position, now we're going to apply Fleming's right-hand rule. I always start getting the direction of my magnetic field first. So we're going to rotate our hand so that our first finger is pointing to the right, right? Now, they told us that the coil is spinning in a clockwise direction, right? And so where current is going, before I get there, I'm going to apply Fleming's left-hand rule to the part of the coil that is closest to the north side of the magnet, right? So that's what I'm applying it to, just so you guys understand. So first find your direction of the magnetic field, north to south. So your first finger should be pointing to the right, right? Your thumb should be pointing upwards because it tells us that it's going to rotate clockwise, so it's up and around, right? And whatever direction that your middle finger is in, that's the direction that the induced current will flow. If you're positioning your hands correctly, then your middle finger should be pointing towards your laptop screen after you have applied Fleming's right-hand rule to the side of the coil that's closest to the north side of the magnet, right? If you're going to apply Fleming's right-hand rule to the part of the coil that is closest to the south side of the magnet, then all you have to do is just rotate your hand because the coil is being rotated clockwise. The side that is closest to the south pole is going to be going down and around. So instead of our thumb pointing upwards, it needs to be pointing downwards. So we rotate our hand, and now your middle finger should be pointing towards you. So current is coming out of the plane of the paper towards you. Second image here was just the right-hand grip rule, not as applicable to the current question that we're working. We're just showing you guys what it would look like. And if we're to draw the diagram of the voltage based on the current position of our coil in the magnetic field, our graph would look like this. Remember, in 0.0 Oh, that should be 0.02, by the way. Right, yeah. So in 0.02 seconds, there should be one complete cycle, right? And so whenever the coil is parallel to the magnetic field direction, you're going to have your greatest voltage. And when it's perpendicular to the magnetic field lines, right, which means it's at top to bottom, then you're going to have 0 volts. So you're just drawing a wave right there. And as I said, we use Fleming's right-hand rule to get the direction of the current right there. And just a bit of side note here, comparing the AC motor versus the DC motor. I'm going to start by explaining how the AC motor works, and then I'm going to explain how the DC motor works. It's going to take me about 2 slides, so we'll come back to this slide shortly. But I want you guys to see the difference in the steps, right? So we're starting off with our AC motor. So in the AC motor, kinetic energy is converted to electrical energy, right? So you have a coil that's not connected to a battery, that's positioned inside a magnetic field, and then you begin to turn that coil. It will eventually produce a electrical current, and that's where you get your electrical energy from, right? And again, we use Fleming's right-hand rule for induced current. So based on this diagram, the coil rotates clockwise. So the side closest to the North Pole is going to experience an upward force, and the opposite goes for the south side. So the south side is going to be experiencing a downward force. Remember, we're talking about the AC motor right here, right? And so using Fleming's right-hand rule, current goes away from you, right? On the side that is closest to the North Pole, it travels away from you. But on the side that is closest to the South Pole, it travels towards you, right? So we need to understand that first. Now, as the coils spin, right, and the coil becomes perpendicular to the magnetic field, we're going to get that EMF of 0 that I mentioned to you guys earlier, right? And to continue the clockwise rotation of the coil, we'll have to apply a downward force to the side that was previously closest to the North Pole, right? Applying that downward force is going to move it towards the South Pole. Now, as the coil rotates, right, the coil is fixed to the slip rings or the commuters, right? And then those commuters remain in contact with the same brushes, right? Essentially, it's just like a terminal in a sense, but it's just in contact with it so that current can flow from the coil to the commuter rings, through the brushes, and to our voltmeter or our oscilloscope, right? Now, because there's constant connection to the same brush, the oscilloscope recognizes the change in direction that occurs when the coil was perpendicular as an alternating current, right? So remember, it's the kinetic motion that produces the alternating current in this case. Now we're going to look at the DC motor, which is the opposite, right? So the DC motor or DC generator, it converts electrical energy to kinetic energy, right? And so you supply an electrical current and it causes the coil to turn because it's operating in a magnetic field. And we're going to use Fleming's left-hand rule because this current is coming from a battery or a cell, right? Now, based on the diagram, current is going to flow from the positive terminal, right? From the positive terminal away from us. So that means it's going to flow through the side that is closest to the South Pole, and it's going to come back to this, come back through the side that's closest to the North Pole. Right? And so if we apply Fleming's left-hand rule, the coil is going to rotate clockwise, right? Which is the same thing as saying that the side that is closest to the North Pole will experience an upward force, while the side that is closest to the South Pole will experience a downward force, right? So I hope you guys are able to draw the parallels between the AC and DC in the coil, and its current causes the coil to spin. Now, the split rings in the DC motor, they're designed in such a way that whenever the coil becomes, they switch contact points, right? They switch the terminals that it's connected to. So if it was previously connected to the positive terminal, it's going to connect to the negative terminal, right? It was previously connected to the negative terminal, it's now going to connect to the positive terminal. And so the side that was previously closest to the South Pole is not trick. And remember, current is flowing towards the negative terminal, right? And if we apply Fleming's left-hand rule, what it means is that that coil, or that side of the coil that's closest to the North Pole, that is now closest to the North Pole, is going to experience an upward force. The direct current again, this is just more diagrams for you guys to look at whenever you have the time. I'm going to be moving on now to the next question, which is transformers. Any questions before we move on?
No question, sir.
All right. Transformers is pretty easy in my estimation. Now, there's not much that I can ask you on this topic. It does operate because of magnetism, but you need virtually zero knowledge of magnetism to answer transformer questions, right? So you don't need to use Fleming's right or left-hand rule. You don't need to use right-hand grip rule or anything like that, right? Even if you didn't know that magnetism was the underlying principle, you could still do the calculations, right? So the transformer is a commonplace technological tool used in our daily lives. Figure 6 shows one type of transformer, and they ask us to label the diagram and then to identify the type of transformer that it is and to state the formula that relates voltage to the number of turns, right? So for A, what is A? A is going to be our primary windings or primary turns. That's correct. What is B? As I'm just waiting for it to correct that answer. B is the soft iron core. That's correct. C, what is C? Even without knowing that this is a transformer, you should be able to tell what C is. Correct? That's our AC supply. Yeah, our AC supply source. And for D, that is going to be our secondary turns or secondary windings. So based on this diagram, what kind of transformer do we have in front of us?
Step up.
Step up. Why is it a step up transformer?
Because on the primary winding there's less turns than on the secondary winding.
Yeah, that's correct, right? So if it's a step up transformer, the secondary windings are going to have more coils on it, right? If it's step down, the secondary windings are going to have less coils on it. If you look at the diagram right here, there are about 4 coils on the primary side. And if you look on the secondary side, that's about 1, 2, 3, 4, 5, 6, 7, 8, right? About 8. Now, you won't use actual diagram to determine the number of turns, but you can see the difference and you can get the intuition that it's a step-up transformer just based on the diagram. And the formula that relates voltage to number of turns is simply the primary voltage divided by the secondary voltage. It's going to be equal to primary windings divided by the secondary windings. So we have Vp over Vs is equal to Np over Ns. The rest of the question gives us a bit more details. It says that the transformer has 5,000 turns in its secondary coil and 50 turns in its primary coil. The voltage supplied to the primary coil is 12 volts and the current is 6 amps, and that's flowing through the primary coil. We're to calculate the input power of the transformer. Now, the input power is always going to be from the side that's connected to your source, right? So it's going to be the voltage and the current that is on the primary or the input side, right? So we have 12 volts on our primary side and 6 amps, and power is equal to current times voltage. P is equal to IV, so we get 72 watts as our input power. Voltage across our secondary coil. Now that we're going to have to apply the same formula that we stated back in the previous question. So Vp divided by Vs is equal to Np over Ns. They told us that there are 50 turns on the primary side and there are 5,000 turns on the secondary side. We know that our primary voltage is 12 volts, and so it's simply plug and chug, transpose, and we get 1,200 volts as our secondary voltage. Again, remember, the step-up transformer increases the voltage. So we're going from 12 volts to 1,200 volts. That's a step-up, right? The number of windings increase from 50 to 5,000. Again, that's an increase. It's a step-up. You can think about it that way, right? Current works in the opposite way, though, right? So To identify if it's step up or step down, do not use current, use voltage or number of windings. Now, part 3 says the maximum secondary current if the transformer is 100% efficient, right? So if it's 100% efficient, it means that the input power is going to be equal to the output power. So 72 watts is going to be our output power. And again, power is equal to current times voltage. We have 72 watts for output power, 1,200 volts. Again, it's plug and chug, and we get 0.06 amps for our secondary current, right? Now, I don't think that there's anything else that CSEC can ask you as it relates to transformers. In this question, they've asked to identify the parts of it, to tell whether or not it's step up or step down, and they've asked to identify the governing equation, and then they ask you about the power of it. The only change that they could probably make is just to ask you to calculate the different currents and what the efficiency was if it wasn't, if you had a particular set of values, right? Now remember, most equipment are not 100% efficient. There is some degree of wastage, right? Heat is most times generated and it's lost to the environment. And yes, I know that the primary purpose of a heater is to generate heat, but it's still not 100% efficient because all the heat that it generates is not being applied to the intended target, right? So some of it is lost to the atmosphere, while some of it goes to the substance that we're trying to heat up. So most equipments are not 100% efficient. And that is the end of the 28th question. Now we're back to 2017 question 6, where we look at and the principal focus of a converging lens and a diverging lens, right? Now, principal focus is the point through which all light rays pass or which they appear to come from. For a converging lens, all light rays pass through that point. For a diverging lens, all light rays appear to come from that point, right? Now, lens isn't a difficult topic. It's pretty much just recall, right? Probably the most difficult thing that they can ask you to do is to do the scale diagrams. But aside from that, it's just calculating distance, height, and magnification. Pretty simple stuff for us to do. So it says an object of height 7.2 centimeters is placed 18 centimeters from a converging lens, a focal length 12 centimeters. We're to determine the image distance, the magnification, the height of the image formed, and to state whether or not it is a real or virtual image. Now, to answer this question, we're going to be using the lens equation, which says that 1 divided by the focal length is equal to 1 over the object distance plus 1 over the image distance. So if we want to find image distance, we have to transpose, so we get 1 over focal length minus 1 over object distance is equal to 1 over image distance, right? We substitute in our equation, just use the symbol, so 1 over F minus 1 over U is equal to 1 over V. The way how I remember it is that object is U, so I'm thinking about it as initial, like initial speed. The image would be the result, so it's final. So I think about it like final velocity, right? That's how I think about it in terms of the symbols. So 1 minus F minus 1 over U is equal to 1 over V. So substituting our values, and it's usually best to work with meters instead of centimeters, right? And so we get 2.778 per meter is equal to 1 over the image distance. Right? Now, it technically doesn't matter if we use centimeter or meter, but the reason I said to use meters is because whenever you're asked to find the power of a lens, it's equal to 1 over the focal length expressed in meters. So if you always express it in meters, it avoids you from making that mistake of calculating the power of a lens with a wrong unit, right? But if you had used centimeters, you'd have still got the same answer for image distance. But I'm continuing with meters in this case. So we transpose, image distance is equal to 1 divided by 2.778 meters, or 0.36 meters. Magnification, we can use image distance over object distance, right? So 0.36 meters divided by 0.86 meters, and so our magnification there is 2. You can also use image height divided by object height to find magnification. We're going to use that part of the formula to determine the height of the image, right? So magnification multiplied by object height is going to equal image height. So 2 times 0.072 meters gives us 0.144 meters, which is our image height. And the image is real and inverted. I said to you guys, lens is pretty much recall, sorry. And you guys just need to memorize the different situations. There's no easy way to tell you how to do it. You just need to remember the different setups for a converging lens. The diverging lens pretty much always gives you a virtual image that is upright. But the converging lens may produce a virtual or a real image. And they usually use the distance. It is the distance of the object relative to the focal length to determine that, right? So the object was placed further out than the focal length, so we're going to get a real inverted image. Right, it's now 12:54. I think we have 1 or 2 more questions left. There's 1 more question. It shouldn't take us too long. Right. So we should be finished shortly. We'll have covered quite a bit of topics. This is our final question for our session, right? So This question is taken from the 2022 paper, and it has to do with Archimedes' principle and pressure. So it says to state Archimedes' principle, and Archimedes says that when a body is completely or partially immersed in a fluid, it experiences an upthrust equal to the weight of the fluid being displaced, right? So the upthrust is not equal to the weight of the body that is displacing the fluid, is equal to the weight of the fluid being displaced. Next question says, a boat which has a weight of 83,000 newtons floats in seawater. If the density of the seawater is 1,025 kilograms per meter cube, calculate the volume of the seawater displaced by the boat. So using Archimedes' principle, the weight of the boat is equal to the weight of the displaced fluid, right? So 83,000 newtons is going to be equal to the weight of the displaced fluid. Now weight is just the force of gravity acting on an object, right? So weight is equal to the mass of the object multiplied by acceleration due to gravity. So we can very easily determine the mass of the displaced fluid, right? For simplicity, we're going to use 10 meters per second as our acceleration due to gravity here. And so we get 8,300 kilograms for our mass. Now we have the mass, and we know the density of seawater based on our question, and so we can easily calculate the volume. All right, remember, density is mass divided by volume. And so volume is equal to mass divided by density. So 8,300 kilograms divided by 1,025 kilograms per meter cube gives us a volume of 8.098 meters cube. Oh, looks like we skipped this part of the question, right? Let's say to define the term pressure, right? Pressure is, again, pressure is force applied normally per unit square area. So pressure, P is equal to F over A. Pressure is equal to force divided by surface area. And pressure experienced by a point in a body of water is equal to the atmospheric pressure plus the pressure of the water above that point, right? So the pressure of the water is equal to rho GH, or density, multiplied by gravity, multiplied by the height of that column of water. And density is 1,025 kilograms per meter cube. Gravity again, 10 newtons per kilogram. And the the height or the depth of the diver is 0.5 kilograms, 0.5 kilometers, sorry, I'm a bit tired. 0.5 kilometers is 500 meters. Now, atmospheric pressure is 101,300 pascals. So we simply just multiply and add, and it gives us a final answer of 5,226,300 pascals, or 5,226.3 kilopascals. So that brings us to an end of our marathon session today, right? You guys should, for the New Jamaica Foundation, on their social media pages to stay updated with the marathon sessions that they have. If you have any questions regarding slides, you can always just send me an email. And this is the schedule of the upcoming marathons that we have.